Hello everyone. Today I'll introduce our work, Inpaint360GS, Object-Aware 3D Inpainting via Gaussian Splatting for 360-degree scenes. Our method enables structured and controllable inpainting, even in complex omnidirectional environments. First, what do we mean by 3D inpainting? Given a sequence of input images, the goal is to synthesize new views of the scene, with selected objects removed. Let's look at a motivating example. Here, the scene contains three objects. The question is, can we edit them without manually providing object masks? The answer is yes. With Inpaint360GS, we can flexibly remove objects and then complete the missing regions in a geometry-consistent way. Before our work, three major challenges remained unresolved. First, the lack of stable segmentation methods to enable flexible object-level editing. Second, most existing inpainting strategies were designed for 2D images, leaving 3D inpainting inefficient and underexplored. Third, the absence of a fair 360-degree benchmark made it difficult to evaluate object-aware inpainting quantitatively. A recent work, Gaussian grouping, tried to bridge 2D masks with 3D Gaussians, but it fails to assign consistent object identities across multiple views. This inconsistency makes tasks like object removal and 3D inpainting unreliable. Their diva-based method fails to assign consistent object identities to Gaussians across different views. In our pipeline, consistent object IDs play a crucial role as they directly enable the inpainting process. We begin with a scene reconstructed by Gaussian splatting. The key challenge is, how do we obtain multi-view consistent segmentation? To address this, we introduce a key object management system. It transforms raw 2D masks, produced by foundation models, into consistent object IDs across views. These consistent masks are distilled into the 3D Gaussian field, while other Gaussian attributes remain fixed. Once we have consistent IDs, we can remove target objects directly. To recover the missing regions, we generate virtual camera trajectories around the removed object so that we can reveal previously unseen areas. Unlike prior methods which rely only on the original training views, often sparse and discontinuous, our object-centered virtual views create smooth transitions which are crucial for reliable inpainting. The identified never-before-seen area can be continuously and reliably recognized. After 2D color and depth inpainting, this area will be used for depth-guided inpainting initialization. On these virtual views, we perform recursive 2D inpainting. Frame T plus 1 is generated conditionally from frame T. This recursive process produces coherent, temporally consistent inpainted sequences. Finally, these inpainted images guide the 3D completion, leading to a consistent and realistic reconstruction. Now, let's compare with state-of-the-art approaches. Our method achieves consistent segmentation. It works not only in single object cases but also in complex multi-object scenes. Even in bird view corner dense case, overall, Inpaint360GS enables accurate object removal and produces high-quality textures with strong view consistency. Next, let's take a look at runtime and model size. In terms of efficiency, on benchmark scenes like bear and kitchen, our method completes 3D inpainting in 2 to 3 minutes, 5 to 10 times faster than previous approaches. It also reduces model size by nearly 30%. To support quantitative evaluation of inpainted views, we collected a dataset of 11 scenes, including 4 with multiple objects and occlusions. In these complex scenes, our method demonstrates stable performance and consistent results across different viewpoints. Thank you for watching.